arriving talking about a biological future. I'm very excited that Lining Yao managed to join us. She's also a current PhD student from the MIT Media Lab. And at that point, I also wanted to say thank you because I was allowed to join her project last summer, and I had an amazing time. And that is also the reason why I actually organized this event, because I learned so many things from the MIT Media Lab, from all the students there, from Hiroshi, Ishii. And I wanted it also that people kind of like have the same chance of this exchange. And she will also show later the output of the project, but she will in general talk about the integration of like a biological approach and how the engineering changes through thinking about biological materials and designing responsive and transformative interfaces, and about the paradigm shift from making to growing. Thank you very much.
So I will make my way here. Since we're talking about biological identities, I'd better not being embedded by this engineered shelf, and I'd better present a biological being, considering it is very small. So I'm sorry if what I'm talking about doesn't make any sense, because I haven't really slept for 48 hours. But I want to make a bold claim before I go with my presentation. I think I'm a very legit person to talk about how MIT students are collaborating with RCA students. Through my 3 years PhD study, I have been collaborating with 3 RCA students. Daniel Tauber, who is from Interaction Department, and Helene I just mentioned. She's from the Innovation Engineering, and we actually also have Oksana, who is from Fashion Department. And she is currently still working with me. Actually, she is now at MIT. So yeah, for my daily life, or daily work life, I design transformation. And this is how I gorgeously looks like behind all the transformation scenes. And these are some of the things I did before. With transformation, you can transform the shape. You can make a strap into an energy-saving bulb shape, and you can transform function. By the way, these are all collaborative work with some RCA students, and Jifei is here, and some other postdoc from Tokyo University who do mechanical engineering, etc. And this is the transformation to achieve texture change. And you can also transform a surface property of an inflated balloon. And with that, you can inflate food. Insanely strange, I figured at some point what I have been doing are very, very similar to how nature transforms. I thought it was an incident at the beginning, because maybe because I was from Inner Mongolia and never saw a computer when I was a child, so I had to always interact with nature. But later on, as I study more and more, I realize it's almost a destiny. As we are striving for more adaptive, more responsive, and smarter objects, artifacts, interfaces, we found we are more and more closer to the nature, because nature transforms, nature reacts, and there are different types of stimuli can make nature react in different way. Some reacts fast within milliseconds, some react slow, all through their lifespan. And I started to ask, what's the next step? I did lots of things that resemble nature, but how about you directly using natural materials? Because they are already so good at what they are doing. Can you just use them instead of trying so hard to simulate or to imitate their behavior? So today, the main project I brought here is called Biologic. It's actually the next step of designing with nature. We call it derivation from nature. And I will start with a little teaser. Yes, so actually what you just saw and what you just thought is right. So we are using cells as the source for transformation. Indeed, this cell has a specific name called Bacillus subtilis natto cell. It is an ancient bacteria that's deeply embedded in the history, culture, and nature. And it was found thousands of years ago by a Japanese samurai during the war. And since then, it had been used to ferment natto food in Japan. So it's edible and very human-friendly bacteria. In our research, we found accidentally a new function of this bacteria. The bacteria can change their body size based on the relative humidity environment surrounding it. Basically, it expands and shrinks when we change the relative humidity. If we think about the concept of an actuator, these were some design sketches of Tesla. When he developed the alternate current, he also invented a lot of electromagnetic-based actuators. And since then, the notion of actuator is tightly linked with the electromagnetic system. However, in our research, we are trying to introduce a new notion of actuator, which is the biological actuator. Instead of manufacturing an actuator in a factory, you can actually grow an actuator in a biolab. So we culture, again, we harvest those cells from nature and then we culture them in a biolab. Within 24 hours, one cell can turn into billions of cells. This is the time elapse we shot all across 3 hours when one cell was under a microscope. Then we put those cells also into an atomic force microscope and really observe and measure the transformation. And here you can see, as we modulate the relative humidity from 0% to 100%, the cell can expand up to 20% of its original body size. And it's a reversible transformation. And then we sort of made the cell into a very high density liquid solution, load it into a customized bioprinter, and starts to print those cells on top of another film to make our smart material. By the way, we did build this printer by ourselves. And it's very high precision. It reaches micron in resolution. The reason you want to do line printing is because this way you can control both the bending curvature and also the bending orientation. With this material, we somehow just accidentally placed on the hand and figured, oh, it's actually hypersensitive to the humidity conditions around the skin. And New Balance got interested and started to help us to analyze all the body thermal conditions. So there are a lot of research going into figuring out where are the parts of the body that heats up and where are the parts that sweat when you are under stress or when you are doing intensive sports. And with all that, we started to develop our biological garment that you saw from the very beginning of the teaser. This garment, we think it from a quite functional perspective. Human being actually has a way to make themselves survive. When you do intensive exercise, your skin gets sweaty because the vaporization of the sweat can take away the excessive heat and make your body cool down faster. However, as the evolution is going on, and now we are developing artificial materials to cover our body, those traditional fabric materials are actually fighting against our natural process of trying to keep our body healthy, because they don't understand your sweat needs to get out. In our case, we are trying to introduce this bacteria who understand when your body needs to vaporize the sweat. In a way, we are trying to develop an ecosystem between a human being as a body, a human being and body for a human being, and also the body of the bacteria on top of the skin. And we are also trying to create an ecosystem between this human body and also the stuff on top of human body. So this is the full dance piece we finally got to shoot with the collaboration of two amazing dancers from Boston Ballet Company. As I mentioned before, we did a serious parametric design to try to map the pattern with the body heat and also sweat distribution. And as the dancers are moving faster and faster and build up the energy, the cells can open up. We're not stopping just by the garment, and we're also thinking what the other scenarios you could use this bacteria actuator. And one application is you can think about different types of stimuli. For example, steam. Steam can also actuate the performance. So your tea leaf now can tell you when your tea is ready. Or you can also try to use heat as the stimuli type. In this case, you can design a transformable lampshade that can be activated by the light and also transform in shape. You could also think about interactive toy. In this way, there's no excessive electronics. You just, by turning on and off the electronic circuit to control this little animal doing its own motion. The toy companies like Lego, they really love it because they think this is completely safe comparing to lots of electronic embedded interactive toys. And for now, actually what I'm really trying to figure out is, now we talk about bio-inspiration, and also we talk about how you can directly derive material from nature for your design. Then what is really next? By going through a PhD education at MIT, one thing you got to learn is definitely to figure out a complex map. A map that people need to take at least 15 minutes to try to figure out what this has been talking about. So I'll try to decouple this a little bit. If we fit out everything, you will see there are two keywords. There are biological approach and technical approach. If by now you get the idea of what I'm talking about here, there are always integration of the two. When we think about nature, it's amazing, it evolves, it duplicates. We don't even know what's going on even at the current stage. However, they are uncontrollable. But technology is good at making things efficient, fast, controllable, programmable. By integrating the two, you can really grow with speed, evolve with efficiency, and also transform with discipline. And we decouple from another angle. Here we see what's the next in terms of biological approach for design. From the bottom, there's inspiration to imitation to derivation. And I really think the next step we should do, or we should consider to incorporate into design, is encoding. We started to try it out already. So here we use the same bacteria, but we are trying to think how you can synthetically engineering the function of the bacteria to make it do more things. And as you can see, it transforms in shape while also changing color. And we can also easily make this bacteria glow, for example. There are lots of MIT professors are very excited to work with us and trying to synthesize and suggest to synthesize different kinds of functions. And the reason we are very excited about using living material is if you consider an interactive system, we always talk about input, computation, and output. And here we again know with a living bacteria, we can use the same concepts, but with a bit of interesting living twig. Also, by using living material, you could think about something that only living things can do. For example, grow, evolve, and duplicate. Wouldn't that be poetic if Cinderella's beautiful shoe can grow as she is growing older? Or would it be funny if all this London classic sculpture can evolve and grow through time as it stands there for hundreds of years? And all those interfaces can be done if you are seriously thinking, combining living materials into your design artifacts. And with that, I really want to thank all the team members. Since we're at RCA, I will highlight the two heroes from RCA. That's Helene and also Oksana from fashion department. And I also think I can't really represent them better rather than just letting them talk. So I'll take a little bit of more time to play a making video when everybody is sharing their own perspectives. The notion of actuator can go beyond man-made systems and enter the biological kingdom. In a biolab at MIT, we are growing our own natto cell actuators. Natto cells were found 1,000 years ago by a Japanese samurai, and since then it has been used to ferment natto food in Japan. In this project, we utilize this Asian bacteria in a new way. It becomes a nano actuator that expands and shrinks based on different relative humidity conditions, such as the humidity level in the atmosphere or the sweatness of the skin.
Cell is conventionally considered as a factory for producing chemicals, but its own mechanical properties is always neglected. Here, we are looking at its unique cellular structure. By absorbing or releasing moisture from its intracellular components, cell can swell or shrink in a second. We culture our own cell in bioreactors. One cell can turn into 10 billion cells overnight. This enables us for fabricating large volume cells in a short time for potential industrial applications.
The question now is, how can we translate the expansion and contraction of the cells into new type of transformations that we want? We started to build up an automatic printing system in which fresh cell can be assembled on a thin fabric. The different expansion and contraction level of the two materials creates a variety of bending behavior in space and time. Here, the biological and digital fabrication processes are united together to synthesize a responsive biohybrid material.
We create our biohybrid film through a printing process. With the micron printing resolution, we are able to align the cells along a certain orientation. The alignments create a hierarchical structure which helps us to program the specific transformational behaviors that we hope.
The biohybrid films coming freshly out of the printer can be integrated into traditional fabric. This way, the composite material still holds the function of reacting to the skin and transforming. However, it becomes much easier to handle for the garment production.
In this project, we are trying to create an interactive feedback loop among human body, biofilm, and the environment. During the research process, we always need to modify the material properties based on our experimental data. And we have to use these properties to explore all the design possibilities of our biofilm. Therefore, we build a design interface which can not only simulate material behavior, but more importantly, give the designers a real-time feedback, creating a seamless connection from experiment to design to fabrication.
In this time, fashion is changing, and this project is part of it. I believe it's time we rethink the way we create fashion and the reasons behind it. Biologic Project enables us to explore new innovative materials combined with traditional garment making techniques. The designs are inspired by the knot of cells responds to different body parts, and that creates really fine, flat movements. The experience of wearing these garments is very special because they come to life once you start wearing them.
In addition to a single bending structure, different printing patterns and material combinations enable us to create more complex transformations. If we embed heating circuits into the substrate, the material gets controllable through electronic signals. And looking beyond the cell's mechanical transformation, we can imagine to incorporate additional functions produced by the cell itself, such as color change, and that opens up a quite big variety of future applications.
We always find the opportunities in conflict between disciplines. We deconstruct old paradigms to create new archetypes. That's transdisciplinary. We are very much excited about this biological project and potential paradigm shift from building to growing.
With that, I really want to thank Miles Pennington actually for really supporting our video making process through Helene's collaboration. Thank you.